Hey everyone, my name is Nicolaus Jennings and I am a PhD student in the Electrical Engineering Department at UTA, and my project is focused on studying the DC arc flash phenomenon associated with electrochemical energy storage. In this case, electrochemical energy storage is sourced from batteries, and these systems are more widely penetrating the civilian and defense markets. As a result, this drives the need to characterize and establish requirements for personal protective equipment for workers who will perform operation and maintenance on these systems. These DC systems, unlike AC systems, employ devices such as batteries, capacitors, photovoltaic cells that cannot be turned off, and as a result, these systems present unique safety challenges. So, the University of Texas at Arlington and the Electric Power Research Institute in Knoxville, Tennessee have recently collaborated to study DC arc flash phenomenon sourced from valve-regulated lead-acid batteries, VRLAs, at up to 930 volts, and lithium iron phosphate batteries, or lithium-ion batteries, up to 960 volts. And the results will be presented here. An arc flash event occurs between two different potentials of circuit that ionizes the air in between them. This ionization of the air produces a blast pressure, blinding light, deafening sound, and intense heat. This intense heat is measured in the form of incident energy and is the primary hazard associated with arc flash fatalities and injuries. Study of arc flash has primarily been focused on AC three-phase systems, producing standards like IEEE 1584 and NFPA 70E. These standards provide estimations of incident energy and recommendations for personal protective equipment in these systems. IEEE 1584 to date does not provide any suggestions or recommendations for DC systems, and NFPA 70E offers few calculations for instant energy in these systems. However, application of these estimations and calculations from NFPA 70E produce wildly differing results. Empirical studies to date regarding DC arc flash are lacking, and those that have primarily been focused on studying DC arc flash models or using AC rectified sources. And thus, evaluation of arc flash hazards in a DC electrochemical energy storage system is necessary to understand the risks electric workers face. The measurement suite and setup shown to you today at UTA is one that simulates and emulates the environment that an electric worker will be performing their work and maintenance in. These energy storage systems employ switchgear cabinets or distribution boxes that do not have the protection of, say, a fuse or current interrupting device. And as well, IEEE 1584 notes that enclosed spaces in a vertical electrode configuration, quote, amplify the instant energy release, meaning that a comparative open air arc in a similar electrode configuration has less instant energy measured than one studied in an enclosed environment. Copper buswork and cables are used to bring the positive and negative potentials of the energy storage system into the box where an arc is initiated. The arc is set across two square electrodes shorted with a fuse wire initially, and an SCR or silicon-controlled rectifier is used as a solid-state switch to close or initiate an arc. We've utilized copper slug calorimeters painted black following ASTM F1959 standard. This standard used to characterize arc flash rating for clothing. These calorimeters are placed at a working distance of 18 inches away, found in standards like IEEE 1584 and NFPA 70E. The study of light intensity measurement, primarily conducted at UTA, employs light measurement devices similar in wavelength response as a human eye. Sound pressure measurement is taken from about 24 inches away from the arc. High-speed video of the arc inside the box is recorded. High-speed thermal imaging is recorded of the calorimeter board. And battery voltage across the gap, and current through the arc is also recorded using an oscilloscope at sampling rates of higher than 1 megasample a second. Our test plan across UTA and EPRI was to study different potentials of batteries. At EPRI, they studied potentials of batteries, primarily at VRLAs of 156 volts, or 12S, or 12 in series, going up to 936 volts, or 72 batteries in series, incrementing in steps of 72 volts, or 6 series batteries. In the experiments utilizing LFP batteries at EPRI, they studied voltages of 480 volts DC up using 160 series cells, up to 960 volts DC using 320 series cells. Gap distance at EPRI was held constant at 0.5 inches, which is 12.7 centimeters. At UTA, DC arc flash experiments studied with VRLAs were conducted at 130 volts DC and 260 volts DC. Using LFPs at UTA, we performed arc flash experiments at 120 volts DC up to 480 volts DC, using a single gap distance of 0.5 inches. At both facilities, voltage and current were recorded throughout all experiments. Instant energy measurements were recorded for at least 30 seconds following the arc to allow for any residual heat to soak into the copper calorimeters to measure. From the valve-regulated lead-acid batteries studied at EPRI and UTA, the results we have are shown here. Starting off with the instant energy, for the instant energy produced from VRLAs, it shows it's very insignificant. However, one result did have a 1.6 cal per centimeter squared instant energy released. Often in the discussion of instant energy, there is a term used, arc flash boundary. This arc flash boundary is calculated in IEEE 1584 and NFPA 70E. This is defined as 1.2 cals per centimeter squared and is associated with the instant energy required to incur second-degree burns on the worker or someone who is present in front of the arc. IE does have a typical positive trend with voltage, and this is most likely correlated with the increase in arc duration. Arc duration in both datasets from UTA and EPRI did increase. However, the arc duration from UTA was much higher than similar arc voltages from EPRI. This is most likely due to the internal resistance difference between the batteries measured at UTA and batteries utilized at EPRI. The sound level and light intensity measurements studied at UTA did not vary or increase much with voltage, and we believe this is due to very low difference in the arc current studied. The LFP data presented and studied by UTA and EPRI is shown here. UTA studied 3 different configurations of the batteries. We studied 4P, 8P, and 16 parallel cells, meaning that we would take a module with 4P20S cells and parallel it up to 2 or 4 times. In this data, we can see that the paralleling count for instant energy does not matter that much, as we have a very high 4P instant energy release and a very high 16P instant energy release as well. This instant energy becomes interesting for LFP batteries at 500 volts. When comparing this to VRLA batteries, we see that even at 500 volts, we do not encroach upon the 1.2 cal per centimeter squared or arc flash boundary. In the case with LFPs, we do, however. Looking at the data from EPRI, we see that their instant energy is much lower at 500 volts, 600, 700, 800, and encroaches closely at 1.2 cals per centimeter squared, around 1,000 volts. Looking at the arc duration, we can see this is correlated as well too with the EPRI data. UTA data shows that no matter what correlation or series string combination we're using, it does linearly increase, with the highest durations measured in the lowest string count. For EPRI, using their lowest string count, we see that they're much lower than UTA's highest string count of 16P. This primarily is associated with their lower arc flash instant energy. Of the light intensity studied by UTA and at our facilities, we noticed that with higher string count, we saw greater light intensity and sound intensity. We believe this is due and mostly associated with the higher current produced in each arc. And finally, just some closing words. So this showed that instant energy likely depends on battery voltage, as this is primarily driven by the improved conduction across the gap with increasing voltage, driving higher currents. Also, we show that for VRLAs and LFPs, the instant energy is significant enough to recommend and require arc flash cooling to protect workers from any incident or hazard present. And more importantly, I think one big discussion from this is the topic about the difference between and characteristics of individual energy storage. So, for example, at the same DC potential shown between the LFPs and VRLAs, we saw much different instant energy and arc flash light and sound produced. As a result, it's pretty important to, as a part of future DC models, to include these in calculations and understandings of how to go forward and estimate instant energy. Finally, the arc durations in LFPs were shorter for the 8P and 16P strings when compared to the single 4P string, which we believe is due to the higher arc current causing the arc to extinguish quickly. Thank you so much for listening to me today. I also wanted to thank my advisor, Dr. David Wetz, and the Office of Naval Research for supporting and providing the grant for this research.